Hi, this is Peter with CalcBook, and today we're going to be looking at a Glulam beam design. So just a quick recap on our approach here. We are using the National Design Specification, or the NDS. We're using the 2018 version, and we have two books that we use, right? We use the NDS spec, and then we also use the NDS supplement. So for the spec, that's going to give us our design procedure, capacity equations, and our general adjustment factors. Also give us our flexure, our shear, our deflection, our compression, and our combined loading equations. Our supplement is going to give us our reference design values, our shape properties, and any additional adjustment factors for the specific species or lumber type. So for this design example, we're going to be using the flexure, shear, and deflection section for the book, and it's slightly different than the timber or the sawn lumber section, We have this CV factor that we have to take a look at, and there's a couple other things that we'll be looking at as well, but let's go ahead and take a look at our problem statement. So for today, we are going to be designing a Glulam beam considering the following properties. We have a span of 20 feet. Our width is 5 1/8 inches, and we'll be determining the depth required. So we're just going to be using all the properties or the sections for a 5 1/8 inch width beam. Our combination is a 24F-V8, and that's Douglas fir, so that means the layups are all the same, and that's going to be considered a western species because we're using Douglas fir. We are in a wet service condition. Our compression edge, the top edge in this case, is fully braced for compression, so we'll be able to ignore the C sub L factor, the stability factor. We're going to be using ASD loading. Our loading, we have a distributed dead load of 550 pounds per foot, a distributed live load of 750 pounds per foot. And like we said earlier, we want to determine the smallest depth possible, the most economic depth of the Glulam to resist the applied loading. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, we've got CalcBook open now, so we're going to click into our NDS 2018. Then we'll click on our member design. Then we'll go ahead and click into our Flexure Design and Shear Design, for beam. That's what we want. Click Confirm. All right, we're going to go ahead and leave our beam analysis tool on. We want to use that. And then we also want to use our load combinations from ASC 716. Then we're going to go ahead and click on our component type, and we're going to go to the Glulam Western dropdown, because we have Douglas fir. And then we can go and look at what specific type or the combination we want. So we want the 24F-V8. And then we want a 5 1/8 width, is what we said. And then we're going to start somewhere around 20 inches deep. That'll get us close, and then we can refine from there once we have some design information. So the other thing we need to do is we need to change our design method to ASD. Click Confirm. And then for load duration, we have dead and live. So based on our table, we're going to use a 1.0 load duration factor. And we did say that we have a wet service condition, So we have a wet service condition, so we have a greater than 16% moisture content. So we want to toggle that over to greater than 16%, and that will automatically apply the correct wet service factor, C sub N, to the equations. No temperature condition, so we'll leave that as is. So I think we've got everything we need defined, so we can go ahead and click into our beam loading. We enter our information here, so we have a 20-foot long beam. Our shear we're going to do at 0 or the end, wouldn't matter, because we have a simply supported beam. Our moment is going to be right in the middle, same with our deflection. And then we'll add a dead load. It's going to be a uniform load, It's going to be 550 pounds per foot, so 0.55 kit per foot. And then we also have a live load of 750 pounds, so 0.75 kit per foot. And then we can toggle over to our D plus L here just to take a look at our diagrams. So I think everything looks good there. That's all we need. So we can click over to deflection. And remember, for timber design, we need to apply a modification factor for long-term deflection or for creep. That's K sub CR. And so for a Glulam that is used in wet service conditions, we need to up that KCR value to 2. So we go from 1.5 to 2 because of the wet service condition, which increases our deflection. So we take our dead load deflection here, we multiply it by K sub CR, and then we run that into our load combination. So our total deflection, D plus L, is 1.2 inches. and our allowable deflection of total D plus L is over L over 240, and that's 1 inch. So we are about 20% over. So we'll come back and adjust that once we've looked at the flexure and shear, and then we can make sure that we are within our allowable deflection. So let's click over to the Flexure Design. We need to update the length of the bending member between points of 0 moment. This is for our C sub V, our volume factor calculation. So for us, right, simply supported beam, it's just going to be the length of the beam, which is 20 feet. And then for curvature, we don't have a curved beam. This would be if it had a curve in it, which we do not. So we'll leave that unchecked. Our buckling length, right, we said it's fully braced, so we'll just toggle that to fully braced. All right, so now we've got everything we need here for moment, right? Our demand is already brought over from the bending diagram. So we have our required bending stress of about 2440 psi. That's just M over S. We start looking at our adjustment factors, right? We set a load duration of 1. Our wet service factor, right, is 0.8 for modulus elasticity, which is where it comes into play. We have our Glulam factor, CV, right? We have as X component for Southern Pine is 10. We calculate our volume factor, which is 0.96. And then we can keep going here. Our beam stability factor is just going to be 1 because it's fully braced. And then part of the interesting part about a Glulam is that we have both CL and CV, but they are not applied simultaneously. So in this case, our CV is less than our CL, so we'll go ahead and use the CV factor of 0.96. So we calculate our bending strength to be about 1800 psi, which gives us a DC ratio of 1.33. So we are over as well with the bending DCR there. So if we take a look at our shear design tab, right, we don't have any other additional factors here except for the shear reduction, which doesn't apply to us. It has to do with non-prismatic members, or if you were doing a member at a connection, then you might have a reduction there. But most of the time, this is going to be a 1.0. So leave that as is, and we have a 0.86 DCR for the shear design, so we're okay there. So we do have a problem with our deflection and flexure design. So we need to go back and increase the depth of our members. So let's up this up to a 21. We're still about 16% over on our bending, so we can go to a 22.5. Almost there, but 1% over, so we'll just go to a 24-inch deep beam, and that puts us at a 0.9 for bending, and that puts us at a 0.64 for deflection. So that works for us. So that is a Glulam beam design in CalcBook. We hope you enjoyed the video. If you have suggestions or questions, please let us know in the comments below, and we'll see you next time.